COSI 5010, April 16th, 2021. Sounds pretty good, huh? Now let me share my screen again. And let's go to OneNote. Okay, so I don't know, I probably should start from scratch on here, but and so that you can, maybe I can try and write a little bit more carefully if you're having trouble with that. But how do you prove, like when you're just doing general logic, when you're just doing logic, how do you prove something exists? Well, you find a witness for the thing, and I should have called this lowercase t here. And so you figure out, it says, oh, there exists an X of type T such that P holds. And how do you prove that something exists? You have to find, this is why existential proofs are hard. You have to actually find the thing that when you replace it for X and P, is there a problem? No? Somebody wants to say something? Okay, I thought I heard a comment. When you want to prove this, what do? You have to find some X, something that's in T that makes P true. You know, like, I mean, you know, you might have, like, as an example, I don't know, do I need to give an example of that? I mean, it might not hurt, I guess. As an example, I could say, I don't know, I'm never going to get done if I have to do this kind of thing, but let's just quickly try to give you some intuition on this. What would I do? Suppose I want to prove, like, suppose the predicate even, which is, you know, nat to bool, is that, you know, even k is equal to, oh, there's a double exists in here. This would be a double exists. There exists a y, which is a nat, such that 2y is equal to k. And then if I wanted to prove from the empty set of, from the empty context, and so usually we just don't write it down. We want to prove, well, we could prove something directly so that I don't have to do a double. I mean, we could say, like, you know, something crazy like, you know, there exists a j in nat such that even j. And so what do we have to do? Well, you might want to unfold j. So let's just prove, that's silly. Let's just prove even 4. And so one step, you can always unfold a definition. And so that's the same as saying, okay, there exists a y in nat such that 2y equals 4. And so this is just a definition of, this is just definition of even. And then this one is exists on the right with a witness. I mean, sometimes, I don't know, it depends, you know, sometimes you say, like, use. And so what times what is 4? Okay, use 2. So then what remains to be shown? Well, you know, in a strictly typed environment, we would better show, first of all, that 2 is a nat, because we want it to be a nat. And that's just true by the definition of nat. And then over here, we got to show that 2 times 2 is equal to 4, and that's just true by computation. And this is true just by, NAT. So like, here's a proof, but we had to choose two. We had to say, what was the thing that existed that makes 4 even? And the evidence or the witness, let me try to write more neatly. The witness for this statement here is 2. The witness for the evenness of 4 is 2. So does that make sense? That's how you prove an existential. So if we go over here and we say, okay, well, what did we do? Well, we showed that the witness had the right type. And then we showed that when you take, oh, and this should be P. This has got to be P. And we replace T for X in P, then if I can get a proof of that, those two things, then I have a proof of that there exists an X and T such that P holds. Okay? Now, what about on the left? What if I've assumed that there exists an X? Now, technically, maybe, we could write this rule in a number of ways, but maybe what I want to do is I want to say, first, let me go back up here and first talk about, now, let's see, what is the extract? What is the evidence for something like this? So I think I'll move this over a bit so I can annotate it with the extract. And I'll write the extract. So what is the extract here? The extract here, let's call it T1. And the extract here, let's call it T2. And so what is the extract here? The extract here is, in fact, this extract doesn't really contribute. You just say the witness T paired with the proof that the witness replacing X actually proves the right thing. So in fact, I could maybe draw this like, okay, maybe do it like in Haskell style, say, I don't care about this extract. Although it needs to be true, it doesn't contribute to the computational content of this thing. Let me make that line longer. And so let me call that one T1. And it's a pair. So this takes a little while to get used to, I think. This idea that, well, it won't update. There we go. Is that, and often you would really see it like, more abstractly or more mathematically. You might write, this one here is rho, where rho is the proof that P with T for X is true in the context gamma. So now, if we take, the reason I said we could write this rule in another way down here is, one way to write it is to just, let me separate this out so that I have a little room to annotate that assumption. with a variable. So if I've assumed that there's some x that has property, x of type t that has property p, what could I know? Well, you could know, if I've assumed that's true, then, maybe, I'm not sure. I mean, the straightforward way to write this is to say, okay, gamma 1, comma, and we know that y has type t. So we're going to choose a fresh y. I'll just say y fresh. And we have a z that proves that p with y for x is true. And then we have the rest of our assumptions. And then we're still trying to prove some formula phi. So this is kind of the straightforward rule. And the thing is that when you assume that there exists an x of type t such that p holds for x, then you get to choose, make one up. Just say, okay, call it y, call that thing y, that's the witness, and do this. Now, I guess maybe what I'm thinking before was, so how do we do an extract on this? Is that we say, suppose that can anyone guess? I mean, actually, you know what? I'm suddenly realizing that doing that makes it look like the empty set. I'll say this, fine. Does anyone have an idea of what the extract on these might be? So this one could be W. I guess maybe that's part of the annotated. Yeah, let me get rid of my W. Whoops.
Sir, could you scroll down a little?
Oh, I am so sorry. Yep, there we go. There exists a y and t such that p holds y's and t. I guess I'm going to get rid of these variables because they're really part of the extracted thing, because we don't need, in the logic, we don't need labels. It's only when we're trying to do extract terms. So you get to assume that T is inhabited, that T is a well-formed type, and then you get to assume that, I guess maybe you need a Y here, though. So I don't know. I'm working in some kind of like middle ground system. I'm sorry this is not completely precise, but Mimram doesn't really cover like extracts at all. But I mean, does he cover? He must do like the. I don't think he does. He doesn't do system F, so he doesn't do like the polymorphic lambda-calculus, which is what the other name for this is, and I'll show you why in a little bit. So what is, part of the what is the, the annotations here? I can add like a W to that, and I'm going to have an extract there, and I'm going to have an extract here. And what's my extract going to be over here? And so I'll call this Z. So if the extract here is, let's say, T, how do I use W? Well, what I want to do is I want to take T and I want to replace Y by pi 1 of W and Z by pi 2 of W. And remember, pi 1 of a pair, x, y is equal to x, and pi 2 of a pair, x, y is equal to y. So this one up here shows you that the evidence for an existential is a pair. And down here, you may need to use this. This thing could be something that you can break apart and use in some way. There exists an act such that, P and Q holds, and then you can break that apart and you're trying to prove Q. So it's very helpful. You need to get in there. So does that make sense? If you know that there's something exists of type T's that makes P true, then you can grab it. Okay, and so the rule here, though, also is that so I'm a little bit struggling on what I do about this. Like, maybe individual. Like, why do I need that Y there? I need the Y for sure to refer to the thing, what the thing over here that is true is, right? So I'm wondering what my contexts have to look like for just the straight up logic. Do I need to number them or something? Give them all variable names or not? So now, suppose that you wanted to write down, suppose that you had, well, let's do the for all rules and then we'll look at something else, okay? Let's do the for all rules. So the first so this is, exists on the left, and you don't need to provide a witness because the fact that you know that this is true means that, okay, just grab, there's something, you don't know anything. One thing that's going on here, though, is that, and this is definitely true, that Y is fresh, is that with Y being fresh, it means you don't know anything. Suppose T was the gnats and P was, even. Well, you don't know which even gnat it is. All you know is that T is a gnat and that T is Y is a gnat and Y is even. But you don't know which one you have. There could be lots of witnesses, right? For evenness, there's, an infinite number of witnesses in the natural numbers. So it's not like the case that a witness is a unique thing. Okay, so let's look at the for all rules. So these are the existential rules, which are the ones that are not included by default in System F and the ones that are not included in Plutus Core. So why did I go there first? Well, I think it's important that these are pairs, to notice that these are pairs. So now let's look at the for all rule. Suppose I want to prove a for all x of type T, some P, maybe I should be writing these like this, P of X, which means that X may or may not occur free in P. So how do I prove a for all if I'm not doing induction? What's the most general proof rule for all?
Isn't it just like any value would fulfill the proof?
Congratulations, Jessa. That's really good. You choose an arbitrary value. And so, you know, now you do have to make sure that you choose a fresh variable. And so we could say, assume that y is something of type T, and now show P of y. It also, depending on, it also seems to me that in new Perl, certainly you would have to show that gamma, you better show that T is actually some kind of type, is a sensible type. And so, thank you, Jessa. You're like so brave. There's all these smart folks here besides you who I know knew the answer to that and didn't speak up. Okay, and so what's the extract? They're probably doing something else. Let's say the extract of this is some T. And I mean, we don't really need this one. Whoops, let me keep writing in red. Or orange, I mean. So suppose the extract of this is T. And the extract of this, I don't really care about. This is just a kind of a side condition to verify that the thing that I'm doing is sensible. And so what's the extract down here? It is lambda x. And if we're in the typed lambda calculus, we would say colon T dot P. Now, maybe I'm like making things more complicated by worrying about, what do they do in natural deduction rules about these variables? Well, they assume you're choosing fresh ones. And so, this is alpha equivalent to, if x is not fresh here, this is alpha equivalent to lambda y colon T dot P, right? Where you replace all the x's by y. I'm sorry. If I write the substitution notation, I go like y goes in for x. What John Cowles would do when he taught logic, I don't know if and even all of you don't know who John Cowles is. He's often in the computer science department, plugging away in his office. He's an old guy. He's retired. He comes in he comes in more than any other faculty member in the department. He sits in his office in computer science, sometimes 6 days a week, working on the ACL2 theorem prover. And when he taught logic, what he would do is sort of say, like, the first thing you do, and this is like Barendrecht's rule, is go through everything you're trying to prove and make all the bound variable names different. And then you never have a trouble with something like this. I mean, you know, we could worry about it and get more technical. And then I say, okay, look, choose a fresh y here. And then, you know, replace, put y for x up here. And then down here, take t and replace x for y. All right, I'm not hearing anything. Does this make any sense? So what do we know? We know that for alls look like the computation, let's say it this way, the computational content of a for all is a function. So if it's for all x colon t dot p, it's a function from t to p. And the computational content of exists is a pair. So exists x colon t dot p is a pair of the kind t comma row. Well, I guess I could just say p. Because row is evidence for p. Maybe I should say, you know, this is the Curry-Howard, I'm sorry, the propositions of types reference. So there is the inhabitant of this thing is a function of this type. If I just translate a proposition that looks like, you know, like this into a type, now sometimes they write it like this to indicate that X is the thing that's coming from T. Now, what about for all on the left? Well, so look, this rule actually looks like the implies on the right rule, except that we have to worry about getting the right kind of making sure that this thing is a type. Maybe we don't even have to do that, because if it's absurd, then we get it. So I think maybe this goes away. That's why I don't need it to use it, because if this t is absurd, then I can prove it using the absurdity of t. Now, am I making a similar mistake up here? What does he do? What does Mimram do on his regular rules? He just says prove exist x of type A, or just prove this. All right, so let me eliminate these, although these would be standard in new Perl. So because new Perl has some other issues that I'll tell you about in just a second that reinforces that. So if this is P, I got to replace X, I'm sorry, P for X. And if the extract is P here, then this is the extract there. Now, the reason we also have these, often have these side conditions in new Perl is because new Perl terms are untyped. You can't, there's no like decision procedure to determine if a context is well typed. So before you throw things over there, you almost always have to make sure that the thing that you're building into the context is sensible. Okay. So those are some proof rules. You can look at, well, gosh, now I lost my page. Where's it? Mimram on 5.1.6. Gives the natural deduction rules for all. And exists. And I don't think, Finley, you've read this book more carefully. Oh, wait, maybe he does go over it. He does. His rules, okay, so on page or section 5.1.1, for comparison, 5.1.11, he adds some special terms. Oh, have we done the, oh, we didn't do for all on the left yet. Let's do for all on the left.
Can you scroll down again, please?
Yes, thank you. For all on the left rule. Okay, so suppose that I have some partial context, and then I have a formula of the form for every x of type t, p holds, and then I've got some more context, and I'm trying to show some formula 5. So if I can show using gamma 1, now I sometimes, there is He doesn't do the secret rules. I'm trying to remember. I think you need to leave this one here. And now if I show that T1, I'm sorry, I don't need have the term. Now I can show that T is inhabited. And then over here, I can say gamma 1, comma, Y is P with T for X. Gamma 2. And that shows phi. So this looks like the rule for implies on the left. You show the, you know, for implies on the left, what do? You show that T implies P. Oh, well, I could just write it down. Gamma 1, comma, T implies P, comma, gamma 2 turnstile phi. First thing you do is you use gamma 1, comma, T implies P, comma, gamma 2 to show T. And over on the other side, then you can use gamma 1, comma, P, comma, gamma 2 to show phi. Right? So this is the implies on the right rule. And this is the for all on the right rule. And so it's reflecting the same structure as the implies on the right, because a for all just becomes like a is a function type. So what are the extracts on this? So I'm going to call this f because it is a function, but I could call it anything, y, z, w, whatever. And suppose the extract of this is t1, and suppose that the extract of this is t2, then what's the extract of this? This is t2, but where every occurrence of y is replaced by what? We want to take f applied to t1. F is the function. Here's something that's of the right kind of input, because we showed that this was t1 is evidence for t. So t1 is the right kind of input to f. So that's going to be evidence for p. And so y was used in extract t2 perhaps. And so I'm going to go through and replace all the y's by applying f to t1. How do you think? So now, one thing to note is that, and what does Mimram say? I just glanced at this, but he said something like, so he doesn't write this. He writes. He doesn't write just lambda. he writes, you know, so for example, here, maybe I need a different color. Mimram writes, lambda for all x colon e. Then he doesn't tag that. That's interesting. So he would write it like that. Oh, it's because we're still not in the. Oh, that's right. Well, he would write T. Okay. So that's a bit on quantifiers. So now, I don't know, somebody, oh, maybe we should do a little, let's just look at like something like, well, first of all, I want to stop sharing and find out how people are. Finn, what are you up to? How's it going? Is this lecture? I mean, have you read all this in Mimram, all this stuff about first order logic? Have you read that section in Mimram?
No, I'm not at that part yet.
Okay.
But it's making sense.
Okay. Kyle. What do you think?
I'm wrapping my head around it, I suppose.
Okay. It is a lot. Wow. This is a lot of material really quickly. Zachary.
Same for me. I'm just following along.
Okay. Well, you know, I don't know. I don't know what to say. I mean, once I took a graduate set theory class in the math department at Cornell, taught by like a world famous set theorist. And I went into the class and I thought I would get it. And then there was a few of us from computer science taking it. There was only like 4 students in the class or something like that. And 2 of them or 3 of them, like, yeah, I think there was only 1 math student and 3 computer science students. We'd walk back to the computer science building and try to reconstruct the argument that we had just heard, where we followed it step by step. And half the time I couldn't do it. But you're still learning, even if you're not able to actually do it this time around. If you end up working in this area, it will, you'll already have some conception of it, whatever that mental conception is for your brain. But anyway, I feel like I actually understand more about Cohen's independent proof of the continuum hypothesis and the forcing method after taking that, even though I couldn't sit down right now and write this extremely complicated proof. So I don't know. I guess I sort of optimistically maybe feel like you're learning something, even if it's not really clicking yet. Simon, what about you?
I mean, I was going to say this at this stage, if I'm going to be honest, I am a little bit lost. But I realise I'm struggling on assignment 8. So the fact I'm struggling on that, and I can catch up with you about that. That's why I'm struggling on this.
Okay. Sujan, what about you?
So I'm not following you, but I will read the related chapter into the Mimram book, and hopefully after rewatching this video recording, maybe I'll be able to follow you.
Okay. Do they teach Buddhist logic in Nepal?
What logic you said?
A Buddhist logic.
I don't think so. There is anything like that exists.
Oh
I
yeah,
don't
no,
know
no,
about
no.
that.
There's a very interesting Buddhist formal logic that actually maybe is more like constructive logic than classical Western logic. It's very interesting logic. I have about 3 books in my office. I often thought of trying to formalize it.
Oh, okay. I didn't know about that.
Mm-hmm. Keegan, thoughts?
I'm just following along.
Okay. You know, this has a direct bearing. I showed Keegan yesterday or day before, I forget now, it's yesterday, I think, that paper on, let me just grab it. Some. I need a new chair. My back is killing me. I love this chair, but man, it is not good to sit in all day long. Let's see. It's called The Ghosts of Departed Proofs. And it's a way of programming in Haskell that uses, you know, Haskell has these for all quantifiers in the type system. And this is a very, very interesting paper on how to annotate with types that you don't actually use, the constructors don't actually use them, but then they're part of the type of the type. You got to put them in. Like if I say list A or either A, B, I could have list, you know, N A, and N doesn't occur anywhere in the list, but the N thing is actually a proof that the list has length N. And so it's like programming with proofs, but the proofs disappear. So when you compile it, since there is no actual occurrence of N in the data type, it just gets compiled away and disappears. But it won't, it'll be a type error and won't compile if you don't have the right entry for A in there. It's a very cool thing. I don't know. I'm hoping we can use it in our compiler to guarantee that the code that our evaluator, that we can guarantee that the evaluation is only on type derivations that have been produced by our type checker. Anyway, Jessa, how are you doing? Where are you anyway?
I'm here.
You're there, but you're somewhere. You're in California?
I actually just moved yesterday. I'm back home in New Mexico actually.
Oh, okay.
So, yeah, that's where I am.
Okay.
But yeah, it makes sense to me. Like I already understand like the logic behind it, but like the definitions are kind of weird, but it's like it makes sense to me.
Yeah, adding the terms is a lot. All right. Ooh, zooming. Okay, can you see this? If I can get back to the beginning. Okay. Can you see this?
It's not readable.
Okay, it needs to be bigger. There is a way to make this bigger. I was just doing it. Yeah. Unfortunately, it's rolling my mouse. um, okay. Now I don't really know how to scroll. Is there a oh, this is weird. Okay, I need to find actually the PDF is what I need. Oh, here it is. Okay, sorry. I was looking at the raw scan files. Let me share again. So what I'm just going to do now is just go through if I can find it. Oh, I guess I can just do it this way. Okay. This is chapter 23 of Pierce. Now, I tried to bring this PDF into OneNote and it just took like a half hour and didn't even upload after a half hour. So I don't know what's up with that. This thing must be huge. So, you know, in the I should say something about let polymorphism. I think I mentioned this once before, but okay. And so now I need to figure out how to get my Wacom tablet going if I'm going to annotate on this. And I don't have that previous chapter to show you, but the idea is that if you, does he say anything here? No. Okay. Annotate. Uh-oh, my tablet's low in power. What does that mean I have to do? I know it means I have to plug it in, but how? I need to add another dongle. Okay. So it turns out that in Haskell, and I do think I might have mentioned this before. If you say like, let ID equals lambda x dot x in ID applied to ID, let's say applied to 2. This works. It will evaluate to 2 for this ID, and then this ID will take that and 2. So it'll evaluate to 2. Now, there's kind of like in a way, let like this is supposed to be exactly the same thing as lambda ID dot. Now take the this as the body, ID 2, and apply that to lambda x dot x. And you'll get an infinite type error splat. Now, why is that? If you think about this, like you look at this, so you look, okay, this one won't do it. I'm sorry. You need to have something like ID applied to ID applied to 2. Now this will work because the identity function applied to the identity function just returns the identity function, and then you apply 2 and you get back 2. In this case, though, what happens? They don't know how to type it because it's kind of, it gets stuck because it says, okay, well, what is the type of this one? Well, this thing here has to be a function because look, I'm applying it to something. So then I've got like, okay, so let's guess that this one is A arrow A. And then that means though that this instance is A arrow A arrow A arrow A. And then that means this wasn't the type. Like, then I must have been wrong about the type for this one. So, you know, okay, now this one must be this type, but then what's this one? Oh, this one is now that arrow that. And so you get this infinite regress in trying to figure out what the type is. What happens in a let, though, in Haskell and in ML, let is handled differently than this, even though this, you know, kind of traditionally in Lisp, for example, this is the definition of let. You know, like let x equals t in, God, I can't write with this thing, P2. So let x equals t1 and t2 is just defined as is equal to lambda x dot t2 applied to t1. And in fact, that's kind of like, I don't know, it's the way I always understood let. That's what it is. It's just a nice syntactic sugar. But in Haskell and ML, what they do is the Hindley-Milner type system actually is powerful enough to let each occurrence of ID that occurs over here, this is occurrence 1, and this is occurrence 2, have different types, even though obviously one has to be an instance of the other. So, and it doesn't matter which way it goes, but I mean, like, if, you know, this type, A arrow A arrow A arrow A, is an instance of the type A arrow A. So that's okay. So in this one, it's a rather, he goes over it, I think, I guess in chapter 22, he goes over the type algorithm and let talks about let polymorphism. And what happens in let is different than what happens in that kind of naive definition of let using lambda. And I think, you know, it was both, and it's another case that's very much actually like what Weiler talked about with, well, Curry Howard, but also actually it's a case like System F. Girard was a logician who discovered System F in logical work that he was doing. And Reynolds is a computer scientist. They're both alive, actually. Reynolds is a computer scientist at, oh, I don't know, maybe John Reynolds may have died. But anyway, he was at CMU. And he independently discovered it and called it the polymorphic lambda calculus, whereas Girard called it System F. And somehow Girard is a great, like, cheerleader for his work. He's a great marketer of his work. There's a whole, you know, I mean, he did a lot of amazing, unbelievable, absolutely earth-shaking work. But somehow, how do we know this as System F? One time, my PhD advisor, Bob Constable, was at dinner with Girard in France, and Chet Murphy had recently done a really amazing PhD thesis in New Pearl. And it was about getting computational content from classical proofs, not intuitionistic proofs. And Girard turned to Constable and said, Chet Murphy's work is some of the most important and significant work of the last decade, or something like that. And Constable said, well, why won't you say that? And Girard said, you do not understand. This is war. So he didn't want to boost up work that was not, you know, his. And so I think that, you know, it could be that Constable did not understand that it was war. Anyway, that's one Girard story that I have. I think it's one of the only ones. I don't know. Thorsten Altenkirk once told me a story about Girard. I'm trying to remember what it was, but I can't. So anyway, the polymorphic lambda calculus treats, or the, you know, the implementation of Hindley-Milner type inference treats lets differently from this naive definition here. And in this, you can type this in and it'll work fine. But if you type this in, which, you know, is the naive understanding that we have of let, it's just cleaner notation. They're not the same. And Hindley was a logician who discovered this at almost simultaneously with Robin Milner, who discovered it for ML, the earliest version of ML. And so independently, you know, they both came to exactly the same thing. Okay. So what he's saying here in this motivation is, look, you know, if you want to use the simply typed lambda calculus, you have to write a different double function for every different kind of thing you want to double. Because you have to annotate it with the actual type. And so this is nat arrow nat, and this is a record with, I don't know, what is that even? In his book, I think that might be a record with one field called L. I don't even know. X is something of that type. I'm not sure exactly what this squiggly brackets is. Does anyone know? But anyway, it's a function from whatever this type is to this type. And if you want to double a function, like you want a function doubler, then you take a function that takes a nat to nat and returns a function nat to nat. And so these all, the types are all instances of one another, but but we have no way to abstract over types in the current system, in the system of what he calls lambda sub arrow. Where does he talk about that? It doesn't have it on here. So, and then he says, oh, look, every, this is kind of like a general principle of software engineering, is that every significant piece of functionality in a program should be implemented in just one place in source code. These all look identical, and yet you have to delete them. You have to do them all over the place. How do I go to the next page? Oh, maybe I have to get out of this mouse. There we go. Come on. Okay. Well, now I got to go back and get that thing so I can clear these. Okay. So he talks about different kinds of polymorphism in here. And I guess one of them is parametric polymorphism, which is what we're talking about in this chapter. And then the other one is, so that's the impredicative. Now, what does that mean? Or first-class polymorphism. Does anyone know what impredicative means? No? It kind of means self-referential, it's self-referencing definition. And this is a good definition right over here. In mathematics, logic, and philosophy of mathematics, something that is impredicative is self-referencing definition. Roughly speaking, a definition is impredicative if it involves a set being defined or another set that contains the thing being defined. So it's kind of a self-referential thing. Now, it's often the case that impredicativity causes paradoxes. So like Russell's paradox is a kind of instance of an impredicatively defined set. It's the set of all sets that do not contain themselves. So it's kind of got this self-referential basis, and that was Russell's paradox, which broke set theory. And then if you look at what Russell did in logic was he made types layered, you know, up a hierarchy, and you have the same kind of thing in Zermelo-Frankel's set theory, is that you remove the possibility of that kind of impredicative definition in, oh God, which axiom is it? Well, I can't remember the name of the set theory axiom, but there's a way to restrict it. I mean, basically it went from a freewheeling world where you could define sets that look like, you know, X, such that, and then some predicate on X. And now the new one is to break the impredicativity, you have to say where S comes from. X and S such that P of X holds. So this breaks the impredicativity of Russell's paradox. If you always have to say which set you're talking about, you don't get like this flip-flop kind of definition that goes back and forth. It's neither, it's a paradox, but it's kind of like if you think it's true, it's false, and if you think it's false, it's true. So it's neither. Now, ad hoc polymorphism is what happens in Haskell when you make an instance of a type class. When you make a type an instance of a type class, ad hoc polymorphism allows you to overload a single function symbol with many implementations. So you could, you know, there's many different instances of the monad type class, or, you know, you could make new instances of the num type class if you wanted to. Like, I don't know, probably there's some kind of interpretation of strings and operators on strings where you could think of that as a num type class. I mean, we do it all the time. We make things instances of the show type class. That's a dead trivial one. It's so trivial that we can tell Haskell, oh, derive this function show for me. And the show function is just a function that, given a type, knows how to turn it into a string. Now, you know, it can't always do it. So like for functions, it doesn't know how, there is no instance of, you can't make it an instance of the show type class. But that's ad hoc polymorphism. So when we make something an instance of the show type class, almost everything you do, unless you're doing some weird advanced types, you know, shenanigans in Haskell, it knows how to derive the show function for you. And so show has all these different types, and what happens is it figures out which show function to use by looking at the type of the argument. And then they index that and they go like, oh, I'm trying to show an integer. Okay, look it up. What's the show function for integer, and apply that one. Or, oh, I'm trying to show, you know, some kind of record structure. Okay, look up the show function. See if you can show that thing by looking up the types, you know, so that you have in there. And if they're all showable, then you could get a show for it. So anyway, that's ad hoc polymorphism. Then there's polymorphism in object-oriented programming type languages and multi-method dispatch and the common list object system. And all right, I don't care. A more powerful form called intentional polymorphism. I really don't actually know what intentional polymorphism is. Now, and then we have Java, which, you know, has the more recent versions of Java have Phil Wadler's fingerprints on them, where there's polymorphism in there. And then there's subtype polymorphism. Which, you know, actually could be quite useful. But we're talking about System F and the polymorphic lambda calculus, which is kind of parametric polymorphism. And you'll see later, I think there's a definition of the theorem. They prove a theorem of parametricity. I don't know. How do you say that? Somebody tried to say that. Paratromicity, blah, blah, blah. It may be one of the last things in this chapter, or maybe it's not here. It's in maybe the more advanced erasure. Parametricity. Parametricity. And then there's a theorem that they show of how parametricity works. So that's why it's going to turn out that parametricity is a property that this type system has, so we can call it parametric polymorphism. All right, I should have not probably gone so far down there. Will that work? Yeah. Okay, so the motivation is to get rid of this. You know, in the early versions of Java, you had to do this. I remember Jeff Van Balen, one of our former faculty members, used to use Java in the compilers class, but it was a nightmare making abstract syntax trees because you had to duplicate functions over and over again. That, you know, because if the type was different, you needed a new version of the function. This would be like needing a new version of the empty list for every different kind of list. Like if you have an int list, you'd have an empty int list. If you have, you know, this without polymorphism, you get stuck in certain things that are kind of annoying. Reynolds did it in 74. Girard has the rightful, you know, precedent on it. It's also called the second order lambda calculus because it corresponds to the Curry-Howard, via Curry-Howard to second order intuitionistic logic. So in the thing that I just presented before, and what Mimram has with his rules, the typing rules associated with for all and exist, there the quantification was over a variable, like, and so that's why we ended up with regular old lambda. In here, what we're going to do is we're going to add a new kind of variable called a type variable. And we're going to be able to write lambdas over that or quantify over that. So we're going to be able to abstract over. So up here in this darn thing, you know, you could write, okay, for every x arrow x, lambda, or let's call it y because I'm using a lowercase x here. For every capital Y, which is a type of, you know, whatever, I don't know, z arrow z, lambda x dot colon y ffx captures all of these functions. I think he mentions that down here, actually. Let's see. Did you go into the double term? So here's how it's written. Let's see. I wonder. Maybe I just want the spotlight. It's a capital X dot T. So the capital X. And so the parameter, the X parameter is a type, not a term. And there's a new form of application, which is T applied to a type in which the argument is a type expression. So the new kind of abstractions are called type abstractions, and the new application is called type application. So here's an example of the new kind of abstraction where you have the capital X there and you apply it to a type. And so what do you get? You get, look at the body T2 and replace all X's by T2. Now, the ordinary reduction rule for abstractions and applications is, okay, if I have a lambda x of type T11 and a term of, so this is a computation term, a term in the computation language, not a term in the type language, applied to V2, we just take the body T12 and replace all the free occurrences of x by V2. So here is an example of the polymorphic identity function. It has type lambda x dot lambda little x big X dot x. And if you apply this to nat, ID to nat, you end up with lambda x dot nat, lambda x colon nat dot x. In other words, it's the identity function on nats. So, you know, like if we went back up to here, we could write, how could we write what's the general type of this? Somebody help me. It would be lambda, let's say, all right, we'll make it a capital X dot lambda f colon x arrow x dot lambda x colon x dot f of x. And so now if I take this, call this double, that'd be a good name for it. Then I can do double nat. Oh God, I can't write on that side at all. Double nat, let me erase that or undo that. Let's see. Then it's equal to double applied to nat. Now, I think they're using square brackets to indicate, is he using that square bracket? So double nat's double nat, double RCD is double with this type, L colon bool. Double fun is double of nat, arrow nat, and so forth. So we can capture all of these with this one. And in fact, you know, you can call it then. You could say like, you know, you could say, so you could say like double, and then you could say nat, and then you could say +1, and then you could say 2, and that should evaluate to what? You do apply +1 twice to 2, and so you get 4. So you can compute with this thing, not just do this to make a new type, but you can actually compute with this. Okay, somebody moan or groan or, you know, I don't know, cry out or tell me, oh, that's cool.
Makes sense.
Okay, good. Okay, so here's the proof rules for these. So this lambda with a capital X dot T2, or the typing rules, I'm sorry, has type for all X dot T2. And at first I thought maybe this was an error where he throws this X over there, and then he shows that T2 better have the type T2. But it's actually not an error. In his rules, now he characterizes these like this. Type application does occur inside these square brackets, whereas regular application, there's no brackets. So this is system F. You know, this is what I think, did Phil say that in his talk? Like, or maybe, I don't know, that this was something that could be written on a napkin, like the, was that in the talk? Does anyone remember?
Yeah, he said Plutus core.
Yeah,
was
could be
developed
written
that way.
on a napkin. And so, I mean, this is part of it. Now, it turns out, though, another extension is going to be to get to F omega, but the first extension to understand is this one. And I think, you know, I can't figure out, like, do I do, so I mean, you know, we're starting with, and we're almost out of time, so I'll just sort of give the big picture at this point, and I'll put this up so you can see this and read this. But we're starting with, like, you know, the system lambda arrow, which is, you know, typed, simply typed lambda-calculus. And now we've got, you know, F omega, or F, system F, which is lambda arrow plus adding in this gray stuff here is the new stuff. Is in the terms syntax, we have ways to, a new kind of term that abstracts over types, and we have an application for types. And, you know, let's skip this for a minute, but it might be, we might have 1 minute to talk about it. And then he adds a new type variable. So these are extensions. These two, adding type variables and adding this type, are extensions to the type system over lambda arrow. And then he extends context. Before, you had terms can have a particular type, but there is no variable bound to a type. It just gets added to the context. That's, you know, at first I was thinking that that rule on that previous page was wrong because he doesn't have a variable attached to X here, but you don't need it. It just means that X is a type. You assume X is a type. And so these are additions. This is plus, you know, I don't know, what do I want to say? You know, abstraction for type abstraction. I don't need to write it down, I guess, but it's just, it's this plus these things, type, which give you type abstraction, and then it gives you evaluation of the new kinds of terms that you added, and it gives you typing rules for the new kind of types that you've added. And so that should, it's just an extension to the existing system, but it's going to turn out to be pretty powerful and very convenient to use. Now, this is not convenient. This is really, you know, like Wilder was saying, like no one in their right mind would do anything with system F directly or system F omega mu directly, but this is a good ground calculus to build on top of. And so this could serve as the core of a nice functional programming language like Haskell. Now, Haskell even goes beyond this, though, with various extensions. So let me just say, even though time is up, let me just say one thing. And this is something that I find confusing is why variables are not values. He only has abstractions. Now, it could be that if you never have a free variable, you never compute down to just a variable. But it seems to me like in here, you could start with some variables. And so why wouldn't you be able to compute down to them? So this I find confusing. And in Mimram, when he talks about values for various systems, he includes variables as a possibility. So I find this a little bit confusing. Now, it turns out this is all presented also in this book by Girard. He is a pleasure to read. He makes so many just kind of crazy comments. And if you go to the front of the WIO courses page for this class and click on the image of this book, that's a full text version of the book. And I think it starts on page, chapter 11 is System F. So if you want to read Girard on System F, you know, I don't know. I haven't, if there's any great little quotes in this section, there probably are, like every section. Yeah. So anyway, all right. Thanks for coming. Any questions?
I don't have any questions, but have you got 5 minutes after this?
Sure.